Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on January 6, 2026, just about 3 days ago. It demonstrates that a large language model, when placed in a self-improvement loop, can evolve into an expert neural network designer, increasing the rate of high-performing architecture designs from just 2% to nearly 97%. The paper is titled, From Memorization to Creativity, LLM as a Designer of Novel Neural Architectures. And, as we'll see later, these results suggest that models can move beyond simple memorization to synthesize hundreds of completely new, viable network structures. Alright, Figure 1 illustrates the core mechanism, which is a closed feedback loop. It starts at the top left, with the large language model acting as a stochastic generator, producing candidate neural architectures. These outputs move into the evaluation phase, where they pass through a strict funnel. The system filters them based on 3 key metrics: whether the code actually compiles and trains, how well it performs on CIFAR 10 after just one epoch, and whether the structure is novel compared to previous designs. Finally, the model is fine-tuned on the surviving, high-quality architectures, preparing it for the next cycle. So, having seen the loop in Figure 1, Table 1 now quantifies exactly what the model learns from. The first row shows the starting point, the lemur dataset, which provides nearly 1,700 initial prompt code pairs. The second row highlights the contribution of the self-improvement process itself. Over 22 cycles, the system synthesized 455 new architectures that met the strict novelty and accuracy criteria. This expanded the final training corpus to over 2,000 examples, blending human-curated data with synthetic, high-performance designs. Well, while the previous table showed the data growth, Figure 2 reveals how reliable the model became at writing runnable code. This chart plots the percentage of syntactically valid architectures across the 22 cycles. We see a rocky start, where the validity rate dips to around 30% in the first few iterations. However, as the model learns, there is a sharp ascent, reaching a peak of roughly 75% at cycle 14. Toward the end, the rate moderates back to about 50%, suggesting a trade-off as the system potentially explores more complex or ambitious designs. Okay, while the previous figure plotted validity, Table 2 breaks down the performance gains cycle by cycle. Focus on the column tracking models that exceed 40% accuracy. In cycle 1, only about 2% of candidates met this standard. By cycle 18, however, that figure surges to nearly 97%, meaning almost every generated architecture is high quality. This shift is mirrored in the mean accuracy, which improves from 28% to roughly 51%. Alright, following those specific numbers, Figure 3 captures the full evolutionary dynamics across 4 panels. The top left graph tracks accuracy trends, showing that while the best performing model, in blue, jumps early on, the average quality, in orange, steadily climbs to close the gap. Next to it, the top right panel visualizes the quality distribution. The green line represents the percentage of models surpassing the 40% threshold, rocketing from near zero to almost 100%. Moving to the bottom left, the bar chart confirms that these aren't just repeats. The system consistently selects novel architectures, shown in orange, throughout the cycles. Finally, the bottom right plots the training data growth, illustrating how these new discoveries continuously expand the model's knowledge base. So, having established the main results, Table 3 now performs an ablation study to pinpoint exactly which components drive that success. The top row shows the full method as a reference. If we look at the bottom row, where the iterative feedback loop is removed, the system collapses. The share of high accuracy models drops to just 4%, and it produces virtually zero novel designs. The middle rows show partial removals. Taking out the novelty filter cuts the number of unique discoveries in half, while removing the accuracy threshold significantly lowers the mean performance. This confirms that all 3 elements, iteration, novelty, and quality control, must work together. Well, wrapping up, 2 main takeaways stand out. Large language models can transcend their training data when guided by non-textual execution feedback, and enforcing structural novelty is critical to prevent the model from just copying what it knows. This suggests a future where AI autonomously designs the next generation of neural networks. That is it for this episode of the AI Research Roundup. I'm Alex, thanks for listening.